Hi guys, this is Mr. Adams from Midwood High School, and this is a video on Table J activity series. Okay, everyone, please be safe, especially my periods 2, 6, 7, 9 classroom students and all my period 4 lab students. All right, guys, what we're going to do today, we're going to look at Table J, right, and the activity series. And if you notice at the top, right, the most active metals tend to be higher, alrighty? And the metals, as you go down lower, tend to be less active. And in terms of Table J, right, what do they mean by activity? It means the ability to lose electrons more easily. So these guys are more easily oxidized, and the guys at the bottom are less easily oxidized. Now, ladies and gentlemen, I marked off the arrow right there, copper and aluminum, because we'll be looking at those two guys today. I was going to do this experiment in class with you, but no problem. We'll do it right now in a second. Before I move on, also, hydrogen, right? Make a note. Hydrogen is not a metal. Could go back to Chem 1. It's not a metal. But on Table J, hydrogen represents H plus, H3O plus, right? In terms of acid, all right? So all these guys, okay, above, okay, these metals above hydrogen are more active than it, okay? And we'll analyze that in a second. Okay, and the guys lower will be less active. Alrighty, folks. So the experiment today involves copper chloride, right, as one of my solutions. Now, the copper chloride solution, right, has two ions in it, copper ions and chloride ions. Now, the chloride ions are spectator ions, and the copper ions are the ones we're interested in, right? So what we're going to do, folks, we're going to take a piece of copper metal, okay, right here, copper metal, alrighty, okay. And what we're going to do, we're going to place that copper metal into the solution. The second setup also has copper, okay, ions in it with chloride ions, chloride spectator and copper ions, which we're interested in. But this time, we will place a piece of aluminum inside of it. Okay. The third setup has aluminum sulfate. And the aluminum sulfate consists of what? It consists of aluminum ions and sulfate ions. And we're going to place this piece of copper solid into the aluminum sulfate solution, and we'll see what happens. Now, guys, before I jump into the results, right, I want you guys to make a prediction in terms of whether setup 1, 2, or 3 is going to react, okay? Now, in terms of setup 1, 2, and 3, are all 3 of them going to react? Or none of them going to react? 2 of them, 1 of them? I want you to use Table J and analyze the situation. Now, I know on your acid and base topic, right, they introduced this activity series table. We didn't get to talk about it much, but we'll talk about it more now. Now, ladies and gentlemen, also one more thing. Before I pause the video and set the reaction into place, I want to make a note about in terms of how do we recognize redox reactions. Let's say you're taking a test in college and there's like, I don't know, 10 seconds left, and they ask a question, which one of these guys are redox reactions, right? And you only have 10 seconds left. Instead of putting oxidation numbers in every last thing, here's a bit of a shortcut. Now, for single replacement reactions, right, we have an element like barium reacting with a compound like copper nitrate, and it gives you copper and barium nitrate. Now, if you have an element on one side, right, on the other side of the reaction, it's in a compound, what's the oxidation number of barium by itself going to be? It's going to be 0, yes? Okay. But when it's in a compound form, barium will be 2 plus. So automatically you know, okay, that's a redox reaction. You're good to go. Now also, folks, elemental synthesis. Okay, now what do I mean by elemental synthesis? We know what synthesis means, right? Two things come together to give you one compound, right? But let's say both of the substances are elements, right? We know the oxidation numbers both will be 0, yes? Okay, but when they're in compound form, they're not going to be 0 anymore, okay? Someone's going to go up, someone's going to go down. So this guy right here, elemental synthesis, will also be redox because there will be definite change of, okay, oxidation numbers. The same thing for elemental decomposition, which is basically the reverse of elemental synthesis. You have a compound, right? Okay, forming only elements, yes? Now the elements on this side will be 0, but these guys on this side are not 0. H is +1 and O is -2, right? So your numbers will be changing. So single replacement reactions, elemental synthesis reactions, okay, and elemental decomposition reactions will always be redox. And we talked about this before. DR, double replacement reactions, are never ever redox. For example, the neutralization reactions and binary ionic reaction with binary ionic. Okay, so here's what we're going to do. Let's take this guy right here, this copper right here, situation 1, and put him in a copper solution. Situation 2, we're going to take the aluminum. We're going to put them inside of the copper solution. And situation 3, we're going to take the copper solid and put them inside the aluminum solution. Okay, and we'll see what happens. Okay, guys, I'm back, and we're making our predictions about these 3 situations with Table J activity series. Okay, so let's go to situation number 1, where we had the copper ions, right? And we put copper solid inside. So let's grab this guy over here and put it over here. I'm doing aerial view. All right. Okay. And we see the solution looks pretty clear. And the copper metal looks pretty much unaffected. We put it right there. Okay, with the solution. So we see, guys, okay, see that? Can you guys see that? Okay. The copper ions look the same, copper metal looks the same. And it kind of makes sense, right? That copper essentially will not react with itself. So copper ions of copper solid, there is no reaction. So if you sort of kind of figure that out, very good. Let's go to the second situation, situation number 2. What was situation number 2? It was the copper ions in solution, right? But this time what do? We put aluminum inside of it, yes? Okay, so let's bring it over here for a second. All right, first, aerial view. Okay, now guys, can you see anything floating around inside on the sides of this small container? All right, let me hold it up a bit, the different way. Okay, I'm swirling it. Okay, I'm going to put the camera a little closer. Do you see anything around the bottom there? Looks like the mossy kind of dark stuff right there. That stuff, folks, is copper. All right, so this reaction definitely took place. Let me take the piece of aluminum metal out, and I'll put it right here. Okay, let's look at it carefully. Okay, can you guys see that? Now look at the difference, folks. Look at the difference between this side and the bottom right here, which was in contact with the copper ions, as opposed to the top part right there that wasn't in contact with it. We see that there's definite change, definite color change, and production of new material, right? So that dark mossy stuff right there, looking stuff, is copper. All right. Also inside of the container. All right, okay, do an aerial view again. You see that stuff swimming around inside? That's a new substance form. That's copper solid, okay? All righty, so we got a reaction taking place in the second solution. All right, so let's try situation number 3. Okay, before I pick it up, what was it again? It was aluminum ions, right, in solution, and we put copper solid into it. So let's see what happened. Let's bring it over here. All right, I'm looking doing aerial view. Solution looks kind of clear. All right, let's take out the metal. Let's analyze it. And the metal looks pretty much unaffected. It's just wet, but otherwise there's no reaction. Okay, so who's brave? Who's going to tell me how come? Okay, there was no reaction in situation 1, reaction in situation 2, and no reaction in situation 3. Okay? As always, guys, you're right. All right? It's all about Table J. Okay? And location, location, location. If we notice, right, in terms of aluminum, okay, it is higher on Table J when compared to copper, right? And let's go through some items right here, guys. Okay, in terms of Table J. Okay, you can make a note of these. All right. Okay. For number 1, right, higher metals. Okay, are more easily oxidized. Okay, they do Leo better. So the higher you are on table J, okay, for example, aluminum, you more easily lose electrons to something, to another metal solution that's below you. Okay, point number 2. For a reaction to be spontaneous. Now, they can give you a question, folks, and ask you, is this reaction going to be spontaneous or not in terms of a single replacement reaction? You don't guess. The solid metal must be higher on table J than the ions in aqueous solution. So let's analyze that slowly. Okay, aluminum here, solid metal. Copper here, solid metal. Solution ions, right? So they're the same thing, right? But what's the difference? In terms of aluminum, right, solid, he is higher on table J than copper ions. So he will take place spontaneously. Now, once again, in terms of copper solid, right, being inside aluminum ions, the copper solid, in this case right here, copper's way down here, copper solid is below aluminum ions, so that reaction is non-spontaneous. Okay, point number 3, we discussed already. Hydrogen on table J represents H plus or H3 or plus, so that represents acid. And you guys did that with experiment with a funny UDometer tube. When you guys put the acid inside the UDometer tube, and the magnesium was in the bottom, and you have to find the mass of the magnesium. So that right there is an example of a single replacement reaction where the hydrochloric acid reacted with the magnesium. Okay, point number 4. Reactions, right, in this topic right here on table J are single replacement reactions, okay? So single replacement is always an element in a compound giving you an element in a compound, okay? And you can tell whether it'll be spontaneous or not based on the location. All right, guys, as we're winding down, please watch the video I'm going to do on this topic again on table J. In that video, I'm going to actually go through different reactions, okay, and show which ones work and which ones don't. But I did want you guys to see in reality what happens when you place the metals in different solutions rather than just talking about it. So I think it's pretty cool right here. See that? Oh, man, nice reaction. Okay. All right, guys, as always, hard work plus sacrifice equals success. Please be safe, take care, and we'll get over this. Take care.